For those of you who have already taken a shot at the week 3 assignment and succeeded, well done. It's well demonstrated in the teaching and learning literature that trying something independently before getting some help for it actually leads to better learning. For those of you who have tried and are still struggling, I'm going to provide some additional hints to help you along your way and get you a little further step by step into getting things to work on the week 3 assignment. So here's our week 3 individual assignment page on OnCue, and you probably have downloaded this archive version which has got a bunch of files in it. Now notice down here that in addition to the assignment, there's also a couple of examples, and we'll have a look at some of those examples in a little while. So having downloaded that, I can go to my downloads folder and find, there's my week 3 archive that I just downloaded. And in there I've got 3 Python notebooks. I've got the individual assignment that we can work on. I've got an example for testing if something's Gaussian. We're going to want to later on test if our BMP 180 noise is Gaussian. Let's have a look and see how we might test if our TMP 36 noise was Gaussian. So I'll open that one up as well. So let's have a look at how this one works here. In our assignment, we can work through the questions in order and give you some hints along the way. I'm going to just move this up here a little bit so that we don't use up all the space on the stuff at the top. In this individual assignment, we've given you some stuff to import, so let's get those imports. And then the question asks, can we figure out a function, define a function called WS, to return the output voltage difference from the bridge as a function of the bridge parameters. So this is a Wheatstone bridge that we've talked about in some of the notes, and we're trying to figure out what this measured voltage will be. Now we can calculate VA and VB based on Ohm's law. We know that the voltage drop across R1 and the voltage drop across R2 will each be proportional to the current that's flowing through this circuit between R1 or through R1 and R2. Those are series resistors. So we'll find out that that voltage A depends on R1 and R2. So the question is, what's the equation for the measured voltage? I would suggest you work that one out on paper to get an equation, then build it into a function. Or you could build the function as you go along. So to do this, we'd need to know how to define a function in Python, and we'd need to have some values to work with. So to define a function, we use def, and the function name, which we said up here was going to be WS. And so that's the Wheatstone bridge voltage, and it needs to have the excitation voltage. That's the input voltage, so VE. It needs to have R1, R2, R3, and R4. And we need to come up with some way of calculating what we're going to return. So we'd like to know what VM is. So for a function, we need to indent to indicate that we're inside the function. These are the statements that will be executed every time we call the function. And for now, let's just set VM equal to 27. Just to have it so that we can return something. We also need a colon up here to indicate that it's the start of a function. And then when the function comes back, we're going to use the value that comes out of the function, so we have to have a return statement. And we're going to return VM. So now if we wanted to have a range of resistances, we could plot out what Vm is as a function, say, of R1. So let's make R1 have a range of resistances. If these were our resistors in our Wheatstone bridge on our load cell, we found that we had about 120 ohms. So we might make R1 a linear space between 110 ohms and 130 ohms. And let's put 1,000 points on it. And then we might make V equal to whatever the Wheatstone bridge function is going to return of, well, 5 volts excitation, and R1 is going to be our R1 that we've just defined, and the other ones could be 120, 120, and 120. So assuming only one of the resistors changes its value, what do we get out as a voltage? And then we could, plot the voltage against R1. So the X value will be R1, the Y value will be the voltage, and let's see what comes out. So we need to run that cell to create the definition. Then we need to run that cell to actually create the plot. Oh, I've made a mistake there. Name error, that should be a PLT, shouldn't it? Because up here, I imported matplotlib pyplot as PLT. Okay. So these error messages are really diagnostic messages. They're telling us where we've slipped up, and if we keep testing our code in small fragments, then we're going to get these messages while we've only got a small piece to look at and can figure out what's going wrong. So let's try that now. Oh, it got even worse. What went wrong here? X and Y must have the same first dimension, but have shapes 1,001. Oh. R1's that linear space of 1,000 things, and when we pass it to our function, because we haven't defined our function with the special NumPy capabilities to do work on arrays, it only returned VM, just a single value, just one value, not an array. So we'd better go over the whole range of values there. So that 1,000, I'm going to set n equal to 1,000, just so I can use n as shorthand all the way through here. So now if I wanted to set the voltage values, I'd better make sure that V has the same dimensions as R1. So V, well, let's start it out just with zeros. We'll create a matrix full of zeros, and it also has to be the same size as R1 if we're going to plot against it. And now I need to go through every single one of the values in V. So I need V with a subscript of I equal to WS of R1 with a subscript of I. So now I'm just passing a single individual value to my function as R1, and it's going to return a voltage value. So if I want to go through each of these, 0, 1, 2, 3 is all the way up to 999, then I'll need a for loop. For I in the range between 0 up to and not including 1,000. Whoops, a colon, not a semicolon. then V of I should be set equal to that. So that'll go through 1,000 different times and set V of I. And now I got a plot, and it's 1,000 different values of 27. So not very interesting. But we've succeeded in defining a function here and returning a value. So let's try sine of R1. And just to see how that works. Oops, I got that sine of R1 is not known. We want to use the NumPy version of that. And now it worked, and I've got a sinusoidal value here. So that's good. I can define a function, and I can plot the results of those functions as a function of how that changes. Now let's puzzle out what's going on here. I can, well, Vm is going to be equal to Va minus Vb. Right? If that voltage is larger than that voltage, then I'll see a measured voltage difference. If Va and Vb are equal, then I won't see any difference at all. So Vm is equal to Va minus Vb. Now I just need to figure out what Va and Vb are. Well, let's figure out what the current is that's flowing through this part of the circuit. V equals IR, or I equals V over R, is Ohm's law. Now, if I wanted to find the current that's flowing through resistors 1 and 2, then I'd need, I'll label that 1, 2 so that I know it's the current flowing through resistors 1 and 2. I'd need the voltage drop across the pair of them. That would be the excitation voltage, the 5 volts minus 0 volts. So that one's going to be VE. And the total resistance of those two in series is going to be R1 plus R2. So I can figure out the current that's flowing through here. And the current is going to tell me something about the voltage. So now how could I figure out the voltage at A? Well, VA is going to be equal to, it's going to be not 5 volts, not 0 volts. It's going to be somewhere in between 5 volts and 0 volts. So it'll be whatever the voltage was up here minus whatever the voltage drop was across there. So VA is going to be equal to VE minus V1. The voltage drop, let's call that dV1, the change in voltage across resistor number 1. So I can get VA that way. Now, if I wanted to get to the voltage drop across R1, I'd need to use V equals IR. That's Ohm's law again, just like I is equal to V over R, V is equal to I times R. In this case, I'm looking at the voltage drop across that resistor. The current, well, the current flowing through R1 and R2, that is the current flowing through R1. So that'll be I12 times R1. And that was the voltage, was the change in voltage across resistor 1. So let's check it out and see what happens here. I've got VA, I don't have VB yet. Well, for now, let's just set VB equal to 2.5. Because if R3 and R4 were equal to each other, then VB would be 2.5 volts. There'd be half of the voltage drop there and the other half of the voltage drop there. So we've worked our way through a process to try to build this stuff into a function. Let's try it out and see what happens. Oh, so the voltage difference goes from a small positive number down to a small negative number as R1 goes from 110 up to 130. Let's see if that makes sense. So we're testing it out with everything else equal to 120 and R1 changing. R1, if it was 120 and everything else was 120, then that would be 2.5 volts and that would be 2.5 volts. And we would wind up with 0 volts. So there's one test case. And at 120, we have 0 volts. So that makes sense. Let's put a grid on here so that we can see things a little more clearly. And sure enough, the lines work out perfectly. At 120, we've got 0 volts. So that one test worked out just fine. Now, if R1 is smaller than 120, then there'll be a bigger voltage drop over R2 that's 120 than there is across R1, which is smaller. So VA will be closer to 5 volts. So the measured voltage, which is VA minus VB, the difference between the two, this is what you'd measure with your multimeter, will be a positive voltage. So this might be 2.55 volts and 2.5 volts, so that would give us 0.05 volts. And sure enough, we see down here that when we get to about 115 and a bit, we get to 0.05 volts. And the smaller R1 gets, the larger the voltage difference is that we measure as VM, the difference between VA and VB. So I think we're on our way to having a function here that works. We're going to have to also include a calculation for VB instead of just setting it to 2.5. And I'm going to leave that one up to you. Now, we've gone through a process-based calculation here to get to VA. If we back substituted I12 times R1 in for that, and we back substituted I12 equal to VE over the resistances, we could probably simplify that to a direct calculation. But I think it's easier to follow as a process here. So let's just put some comments on that process. This is the current through R1 and R2 in series. And this is the voltage drop across R1. And this is then the voltage of point A. So that makes it a little clearer to figure out what's going on. And this is not taking R3 and R4 variation into account. Need to fix. So adding comments like this as you go along can really help when you come back just a little bit later to figure out what's going on. And finally, the measured voltage on our voltmeter. So measured voltage is a difference between two absolute voltages. So those are all things to keep account of. So here's how you can define a function and then use that function to calculate some values and see how something varies. Now, what else is it asking us in this question? Define a function, did that. Plot the measured voltage as a function of R1 for a large range to show any nonlinearity. Well, is that a large range? Can we see any nonlinearity there? And then plot it for a more typical range over that should be 1 part in 1,000. So I'm fixing typos as I go along in these assignments because I'm trying to give you some stuff that's just being newly developed, and I apologize. We're getting it right as we go along. So range of more typical strain gauge resistances that change in the order of 1 part in 1,000. So when we measured in the lab, we saw it was 120 ohms plus a really small bit, or 120 ohms minus a really small bit. And let's have a look at this. Does that look like a straight line? Looks like a straight line to me. Well, plot it over a large range to show some nonlinearity. That is a pretty large range. We went from 110 to 130. Let's try going from 50 up to 180. See what we see. Oh, now I'm starting to see some curvature. So there's definitely some nonlinearity here if there are big changes in resistance. But let's go back down to something small. 119 up to 120. 121 maybe? Okay, so that's looking a lot like a straight line. And how could we test if it was a straight line? Well, we could get some values and actually draw them out. But I'm pretty confident in saying that that's a straight line there. So we still haven't done this with our function defined to actually allow for different variations in R3 and R4, but I'd like you to test that and draw your own conclusions.